compressed gas or liquefied or, for better density, or can be absorbed or adsorbed in various media, and in particular in metal hydrides. So as a form of solid storage. And basically you just release the hydrogen gas from the metal by heating it a little bit. Now, how do we pick a material to do the storage, to absorb hydrogen? Well, basically we'll evaluate it in terms of its gravimetric energy density, so kilojoule per kilogram, or volumetric energy density, so kilojoule per liter. And so various materials and technologies are here. This is compressed hydrogen, this is liquid hydrogen, and these are the DOE targets for proper use. But there are other constraints as well. So, for example, lithium boron hydride seems perfect. However, this material is highly flammable, so there's some safety issues here. Magnesium hydride is up here. So just pure magnesium is actually a perfect carrier for hydrogen. Problem is that you have to heat it a lot to release the hydrogen because it's too thermodynamically stable. So we need to find a material that both has a decent density of hydrogen in it, but is not too stable, so that we don't have to provide too much energy to get the hydrogen back out of it. And also, reaction kinetics, so how fast are we able to extract the hydrogen from it. So this is usually how we conceptualize the process of absorbing and desorbing hydrogen into the material. We can plot these PC graphs, so pressure, concentration, isotherm graphs. So basically, we have this, so in terms of hydrogen and pressure, as a function of temperature, we will have a different plateau at which the absorption or desorption occurs. And typically we'll plot this in these Van Hoff diagram, where plot the inverse temperature versus pressure. So this line represents the point at which there's a transition from from hydrogen as gas to hydrogen absorbed into the solid. So and the slope, so the slope and the axis of this curves actually depends on the absorption enthalpy and entropy. So basically, on this slope, this is the point where the net free energy change from the gas to the solid form is zero. So by setting this to zero, we'll can isolate separately the enthalpy and the absorption entropy. So experimentally, we're able to measure that, which is pretty amazing. And so this is what we're trying to compute. So to be able to basically determine what will be the operating temperature and pressure of this material, we want to be able to predict the absorption enthalpy and entropy. Right. So we're interested in these class of materials, these E2B7 alloys. So these are these structures typically composed of 3 or 4 different elements. So there are magnesium, nickel, and some rare earth components. So these are interesting because has relatively large hydrogen absorption capacity. So over 2% is deemed commercially viable, and it has a low operating temperature. So below 500 Kelvin is good enough, right? So these are some experimentally measured Van Hoff diagrams. So we know the the enthalpy and entropy of the process. Now, so how do we compute these finite temperature properties of solids? Here are the most traditional method. In general, you would want to compute the phonon spectra because that's what gives you most of the thermodynamics. So the most basic thing we can do is just computing the phonons within the harmonic approximation, so that we can do from DFT or DFPT, the perturbative extension of DFT. But this is only harmonic, and so for materials containing hydrogen, we expect the Born-Oppenheimer surface to be highly anharmonic. And so in this case, there are several methods to compute phonons with anharmonic effects. So all of these methods, we call them effective harmonic canonical sampling. So basically, it's we try to map this system onto a harmonic Hamiltonian. So we sample the configuration space with Gaussian functions, basically, and we fit some phonons. So this is quite successful actually for many materials, but it's still not the full picture because it works for systems that are moderately anharmonic. So this is lithium, for example. And if you want the full picture, you would go into AIMD, so ab initio molecular dynamics. This is the way to really sample the configuration space of the atoms. So what we did for this material is actually the most naive approach, basically the harmonic approximation. First try, so I had a master's student work on this, and it's quite simple what we do. We compute the material without hydrogen. We add the hydrogen randomly, and we let it relax to the absorption size and compute the thermodynamical properties. So we know the properties of the H2 gas in itself. This is easy to compute, and then we compute the change in enthalpy and entropy. And for the enthalpy, we're actually not too far from the experiments. At least we're on the right order of magnitude. But for the entropy, not so much. So in particular, so these values don't give us the real picture. In particular, we don't get negative free energy change. So from the calculation, it just doesn't happen. All right, but we know this is the most naive approach. It tells us that basically our harmonic approximation is deemed to fail, and really how we should conceptualize this. Hydrogen is more like a gas within the solid, right? So we really want to let the hydrogen wander around, explore different absorption sites, and compute the full entropy of the system. But this is hard to do. All right, so this is why we turn to this method, which I'm going to present. I don't have a lot of results yet, so I'm going to spend some time on the method here. So MLAX is the name of the method, but it's also the software that we're developing and planning to release very soon. This is the big picture. We use machine learning interatomic potential, so MLIP, to do classical molecular dynamics, as well as DFT. So basically, we'll do a DFT calculation and then let the system evolve through MLIP. So we fit the potential. So we let the system evolve for 100 or 500 MD steps, and then we redo another DFT calculation and we update the MLIP on the fly. So we're using Abinet for the DFT part and LAMPS for the MD. by the way, I'm a longtime developer of the Avenid software. If you know, it's open source. If you're still using VASP, I recommend that you give it a try. Right. So this is the workflow basically. Start with structure. We use ASC on, you know, to glue all of this together. So perform some DFT calculations, fits the MLib, and then let the sim evolve through MD, compute some properties, and evaluate if we are converged, and cycle through this loop. And I'm going to explain this diagram. Right. So formally, how do we conceptualize this? So all right, consider a system of atoms at temperature T, described by the coordinates R. So R is coordinates of all the atoms. And if we want to compute some observable that depends only on the position of the atoms, so this is what we do. We do a thermodynamical average, and P will be the probability of being in a given configuration. So to the minus beta V of R is the potential that we can compute from DFT. And yeah, Z is the partition function. Okay, so then we have a surrogate potential, surrogate system. So we'll say that DFT will be the reference system, and the MLib is the surrogate system. And so we have yeah, the MLib potential, and here we use the expression for a linear potential. It's really just a linear combination of a bunch of descriptors. These are D's, and gamma are the parameters for our potentials that we are trying to fit. Right. So we say we have K of these descriptors. So this potential will have its own probability distribution. Okay, that we call a Q of R, and its own partition function. Right. So we define so this is the Kullback-Leibler divergence, and so this expression, so grades of Q log of Q over P. This is a measure of how different Q of R and P of R are different as probability distributions. So it's easy to show that this integral is strictly greater than 0, or equal to 0. And if it's equal to 0, it means that both distributions are strictly the same. So it means that we can find our parameters by minimizing this function, this Kullback-Leibler divergence. Now, working out this expression, we can rewrite the KL divergence like this. So by expanding the ratio of the distribution probability, we can write this as a difference between two free energies. So the Helmholtz free energy of the reference system that we can compute by EFT, and F tilde would be well, what we can call the trial self-energy. So it's a log of C tilde and plus this term, the average of the difference of the potential. And so because the KL divergence is strictly greater than 0, then we recover actually the Gibbs-Bogoliubov inequality, which is a well-known identity in thermodynamics that tells you that you know, if you have a trial self-energy, a trial free energy, it's going to be always greater or equal than the real self-energy of the system, and you can fit the parameters by trying to minimize this free energy. Actually, when I learned this, I was flabbergasted because this concept of minimizing the free energy, it's actually the same that we use to go back when I talked about this these quasi-harmonic approximations where we try to fit harmonic phonons and to look like harmonic phonons. So we use the same concept of minimizing a trial free energy. And I was amazed to see that the very same idea applies also to fitting MLib. Maybe some of you are very familiar with this, but okay. Right. So there's something called did I skip a slide? No. Okay. There's something called the Fisher divergence. So basically, it's the gradient of the Kullback-Leibler divergence with respect to some parameters. Am I missing? Oh yeah, no, sorry, I'm going ahead of myself. I'm not there yet. Sorry, this is just the expression for the minimization of the KL divergence. Okay, so the gradient of the divergence with respect to the MLib parameters, I want this to be equal to 0. This is the expression. I can show that this is the expression I have for this gradient, and so I can just isolate my parameters vector like this. And actually, this expression is really the same as for linear regression, basically. Yes. So again, so this is specific for linear potential. But okay. Yes. So the Fisher divergence. It's defined like this. It looks a bit like the KL divergence, but here we're taking the gradient of this log with respect to some parameter eta, and eta is either the atomic positions or the cell strain, so the deformation of the cell. So in the case, so if we take the gradient with respect to the atomic position, we can show that this is actually computing the difference in the forces between the reference and surrogate system. And if we take the gradient with respect to cell deformation, this is the difference in the stress. And so we can construct some cost function with assigning some weight to the difference in energy, forces, and stress. And we're trying to minimize all of this together. And we can choose if we put more emphasis on force or energy. Okay, so this is the expression that we would get. So when we discretize the whole thing, so we say that through our molecular dynamics simulation, so we're doing Langevin dynamics here. Say we have n different configurations that we computed by DFT and also with the surrogate potential. Then we can construct this vector, its reference vector, that is 3 n atom plus 7 long. So that means for each calculation, so 1 element for the energy, 3n for the forces, and 6 for the stress tensor. Right. All right. We have our weight matrix, so we have some weights for energy, forces, and stress, but also for each of the different configuration. And so the vector parameter that minimizes this is just going to be this expression. So it's the same expression that I showed before. X here, X is the feature matrix. So 3n plus 7n times k. So for each of the different configurations, the energy forces, we have the contribution of each descriptor to this quantity, right? Right. So yeah, when I when I saw this, my first reaction was, wait a minute, this is not machine learning. This is just linear algebra. And I still think that, but the whole concept, the whole idea applies to, other kinds of MLIP, not just the linear ones. All right, so let's put this in practice. So my collaborators have applied this method to compute the phonon spectra. So basically to sample the configuration space and fit some effective quadratic Hamiltonian to get the full phonon spectra. And so this is what they get. So MLAC agrees very well with full AIMD in this case, and in principle it should be better than the harmonic sampling. So those Gaussian sampling. So AIMD is really the reference here we're trying to produce. So it fits very well for silicon and zirconium. Zirconium is known to be an harmonic, so it's quite relevant here. Okay, so that works. Yeah, reweighting the configuration. So one more detail here. How do we assign the weights to each configuration? So as we refine the descriptors, as we compute a better potential, we can recalculate the weights that we should assign to previous configurations that we visited. So this is the expression for the weight. So at step I, this is the weight of a previous configuration n. So we know what was the configuration, the position, and we can compute the thermodynamical weight with the latest set of MLIP that we got, and we divided that. We divided this with the probabilities computed with previous sets of coefficients. And what that does is putting more weights on the most relevant configuration. So if a configuration, in a previous step, we thought that it was very likely, but with the later step, with the better trained potential, it turns out that it's less likely, then the weight will be reduced a bit, and vice versa. And so this is how this is performed. This is a fitting. So these are the MLIP forces as a function of the true DFT forces, and the color shows you the weight computed with this Bennett acceptance criterion. So as the simulation progresses, those configurations that are most relevant get assigned a higher weight, and those are the configuration that fit better. 5 minutes, all right. Okay. All right, so just few results that I got for magnesium. Right, so these are the parameters that I set for the calculation. We need some kind of supercell, and then these are the MLIP parameters and the description. So we use snap descriptors here, and then we're doing 500 molecular dynamic steps for each DFT calculation. And this is how the energy forces and stress compares between the surrogate potential and the reference one. So there's a very good agreement overall that we get, so we can compute the mean absolute error here, and it's very few outliers, but it fits. And finally, so here I'm showing the convergence on the mean total energy of the system. So this is AIMD, so it's extremely costly. So we need over 7,000 steps for the energy to converge. And if we do it with MLAX, then it's actually extremely fast. It takes less than 200 steps because we get a very good sampling of the configuration space. So I was quite happy with that. The numerical value agrees very well. And here I'm plotting the probability distribution as a function of energy, right? So basically this is a histogram of all the configurations that I get, right? So I bin them by energies. This is AIMD. This is MLAX. So this is the histogram that I get for only the DFT calculations that I extract from the simulation. And then, so I don't have that many points. So it, kind of looks like the original configuration, but then at the end, I can take the trained MLIP and run molecular dynamic simulation to get a smooth distribution. And this is extremely fast. I ran this on my desktop computers just a few minutes. So the values for total energy agree very well. Basically, the error that we get from training MLIPs is actually smaller than the statistical error from the sampling. So this is very, very good, very, very promising. And I'm going to end with something that doesn't work so well. So I added, I looked into magnesium hydride, but MgH2. So this is kind of the maximum amount of hydrogen you could put in the system. These are the parameters. When you look at the fitting, it's not that terrible. Okay, maybe the stress doesn't look so good, but I don't care about the stress in this case. I care mostly about the energy and the forces. And fitting, the error kind of looks okay. Actually, so 0.023 EV by angstrom, this is pretty close to the accuracy that you expect on the forces just from the DFT calculation, right? However, the probability distribution doesn't look so good at all. So actually it seems smeared out. And even if I run the MD simulation at the end, distribution doesn't quite agree too well. Right? The error is larger than I would like. So why is it not working? Actually, I don't know yet. I'll figure it out. Maybe there's a problem with the DFT calculation. Maybe the snap descriptor just isn't good enough for what I'm trying to do. Admittedly, this is harder to do than most of the things. So if I just wanted to sample the space and fit some phonons, probably that would work just fine. Because in the end, I would do the calculation by DFT. But here I'm really interested in sampling the whole configuration space to get thermodynamical properties, and it's kind of a difficult test for this system. So all right, we're working on this. So I haven't tried other types of MLIP yet, but the software, the MLAX, works with moment tensor potentials, should be better. We're currently working on implementing also the AC types of MLIP, so atomic cluster expansion. We've got capabilities for thermodynamical integration, which is another way to get the free energy of the system, so that we should try very soon. And eventually we're trying to move towards doing also a grand canonical sampling. So adding and retrieving atoms stochastically to get the free energy of the gas. So yeah, that's it. I'll end here.
Thank you very much for the presentation, and I have a few questions.
And you stress the issue of possible problems due to the lack of accounting for anomalicity related to hydrogen vibration. The issue is hydrogen is, of course, the bond of climate. So this was still within the bond of climate, which maybe a harmonic with the relevant range of energy. But the elephant in the room is that, of course, if the all breaks down and you have a wave vibration of distinct wave function distribution.
Yeah.
Because the issue may have never been the anomalicity, but rather the breakdown of.
Yeah. Yeah, that's a good point. Actually, I forgot to mention it, but we can also do PIMD with this method. And yeah, you're right. In the case of hydrogen, we should really treat it as quantum, do the whole thing. Yeah. Yeah.
Can you get one more question and then move on?
I just want to mention, this is really interesting. There was recent work, I just talked to the author on the fixing the atomic cluster expansion to get this specific hydrogen in water.
Yeah.
In a bath interval.
Yeah.
It's not too, but it seems it works.
Okay.
Yeah,
Okay.
I was quite impressed. Yeah.
Okay, that's good to know. Thanks.
I think that this hydrogen, you may, I don't know whether it's necessary, but the hydrogen will have a very high thermal vibration. Like they cannot stay frozen at a particular location.
Yeah.
Even at the zero case, there's still vibration, like the 0 point vibration.
Yeah.
Maybe that may cause some different. And also, when you say the energy, do you directly say the energy is from the energy, or do you say there's an energy difference between your system and isolated energy? Which energy do you use?
We fit the total energy
Like directly?
directly. Yeah, yeah, the actual total energy, even though,
Maybe it's easier, like you say the energy difference.
but actually, so the mean energy is actually easy to fit. So it's basically it's almost the same, I would say, because the mean energy. So in the parameters, there's a parameter for just the average energy, and it's practically equivalent to fitting the energy differences. I think.
Okay, I'd like to thank the presenter again.
Sure.
And